So good afternoon to all of you. This time I am again be back in discussing some more extra topic. That will be the last topic from my side, because approximately I can say that whole of the course is being finished from our side. Some of the topics we can say that has been left will not be covered in your exam also. I'm declaring that the circle diagram we have not covered, so it will not be covered in your examinations. But the rest of the topics, and the I am also from the last two lectures I am discussing the Oza sir part also, so that will be also covered in your examination. So today the topic will be the Rankine cycle. So that will be again the Oza sir part of the first chapter, that is the prime mover. In the last week I have also shared one more PPT along with you, that is on the types of turbine and the based on the pressure and the based on the flow path. That is also the part of the prime mover only. So in the today's topic Rankine cycle, what we have to discuss, coming to the contents that we will be discussing over here will be the introduction to entropy, thermal power plant based on the Rankine cycle. This is a very easy topic we can say, because it is quite related to the thermodynamics that you have already gone through in your 12th standard or 11th standard. And it is all this topic is also related with thermal power plant, and as I know that in both the divisions A and B, thermal power plant is being finished in a very rigorous manner by Professor Bhuvanesh Oza. So I must say and I must believe that you all know about the thermal power plants in a very deeper manner. So I will be restricting my discussion of today's lecture only on the Rankine cycle, how Rankine cycle is being used in the process of thermal power plant, in the process of the electricity, in the process of the, you can say, the recyclability of your steam and water cycle. So it is not, this lecture is not quite related with the electrical engineering, but the Rankine cycle that is being utilized in the particular thermal power plant should be also known by a particular electrical engineer, because it is the most important part that is being used over there for a particular generation. So starting with the first topic you can see in your slides, that is entropy. What is entropy? Entropy, in a very layman language, we can say it is nothing but the measure of uncertainty and randomness. Uncertainty and randomness means entropy is nothing but it is the ratio of energy change per unit temperature. I am again repeating, it is nothing but the ratio of heat change upon temperature. You can write it as S, because we always used to represent entropy with capital S. So capital S can be written as dq by dt. Okay, I think I am clear that capital S, which is being I am again repeating that entropy, which can be represented by capital S, it is equal to dq by dt. What is dq? It is nothing but the rate of change of heat, that how much we are adding heat, how much we are taking out of the heat. So there should be some external means through which we can add heat, and there should be some external mean through which we can take out the heat. So if we are not adding heat, if we are not taking out the heat, the entropy will be always turn out to be zero. So if we are increasing the temperature, and if the latent heat, because that heat we are talking about, we are talking here about is the latent heat. So if increasing the temperature, latent heat of a particular fluid increases, obviously entropy will going to increase. So if temperature increases, latent heat of a particular fluid will increase, it is sure that entropy will going to be increased. So in a very simple layman's language, if I want to discuss in entropy, as I have said earlier, it is nothing but the uncertainty, it is nothing but the randomness. So if it is uncertain, if it is randomness, so we can say as the number of molecules are more far from each other, we can say the randomness is high. So if I am talking about the ice cubes, entropy will be less. So if I am talking about the water molecules, water vapor or water particles, we can say the randomness will be high, so entropy will be high. If I am talking about the steam, entropy will be again high. So again you can say that if I am giving certain amount of heat, due to which the latent heat changes, ice turns to water, water turns to steam, and again as we are giving heat inside it, we are inputting the heat, we are changing q, that is dq by dt. So hence entropy is changing. And again we can say if randomness will increase, if the motion between the molecules will going to increase, intermolecular space is high, excitement will be high, and randomness will be high, entropy will be very high. This entropy will going to play a very crucial role in this particular lecture. Again you can read this line which I have already discussed in the previous slide, is that if you increase the temperature, you will going to increase the entropy. As simple as that. Always you have to study these thermodynamics topics in a very simple language. So what I have said, if you are increasing the randomness, if you are how you can increase the randomness, you have to just increase the latent heat of that particular fluid. How you are increasing the randomness? If you are increasing the latent heat of that particular fluid. So if you are increasing the temperature, randomness is increasing, uncertainty is increasing, and hence entropy will going to increase. So I am again repeating those lines which is written in this particular slide, is more energy put into a system, you should concentrate on this, more energy put into a system excites the molecules, and the amount of random activity will going to increase, and as a gas expands in a system, entropy increases. So what I have said earlier, I have already discussed in the last slide. So if when liquid becomes a gas, if your water is changing its state from water to steam, it is going in another state, it is taking heat from the outside, there will be a change in capital Q, that is nothing but the heat exchange. Its entropy will going to increase because randomness will be very much high in gas as compared to liquid. Okay, coming to the next topic, that is the main major topic of this particular lecture, is the thermal power plant based on Rankine cycle. So your whole of your thermal power plant is quite based on the Rankine cycle only. It is quite familiar to you, the figure 1a. I am starting with the figure 1a. So all of you concentrate on figure 1a. In figure 1a you can simply say, so if I want to talk about the thermal power plant in a very basic manner, what I need, what all essential components I need. The essential components that I need is nothing but the boiler. You can see the boiler, because the basic principle if I want to talk about in the thermal power plant is nothing but I want a steam, I want a water, I want to heat it at a particular high temperature so that it will be converted into steam. That steam I will going to feed into a turbine. In turbine, the turbine will going to extract the energy out of that steam so that it will be their blades will going to rotate. After extracting the heat, that steam will not be of any much of use, so we will not be going to release it out in the particular environment, because it will going to increase the global warming of the particular environment. So what we will be doing, we will be feeding it back into a condenser. There it will be cooled again converted into a particular water, but at a low pressure, because temperature is being reduced, so pressure will be low, at a low pressure. And then there will be a feed pump which will going to increase the pressure, and it will be again fed back into a boiler. It will be again fed back into the water. So this process, which is you can see, is a closed loop process. This process that you can see, it is written in the system boundary, it is a closed loop process, because you can see that the path 1 which is going into a steam turbine, then path 2 is going into a condenser, path 3 in feed pump, and again it is feeding back into the boiler. So again discussing the figure 1a, the some points has been written in the next slide. First we'll discuss that, and then we'll going to come back in figure 1b. So again you should remember that block diagram. So where we are discussing about the part between 1 to 2, that is known as isentropic expansion. What is isentropic expansion? Because from 1 to 2 path, in between 1 to 2 path, when your high superheated steam is going into steam turbine and it is coming out to the steam turbine, there will be no change in the entropy. So again you see, if we are traveling the path from 1 to 2 in which steam turbine is coming, that path between 1 to 2 is known as isentropic path. Why it is known as isentropic path? Because there will be no change in the entropy. Now you will say, why entropy is not changing? Because what we used to assume ideally, that in a turbine there will be no loss of heat. In a turbine there will be no loss of heat. As there will be no loss of heat, you are not giving heat from the outside also, so the change in heat or the heat exchange is zero. So as you are not giving any much amount of heat from the outside, you are not taking out any heat because it is a lossless structure where no loss can be occurred ideally. So we can say there will be no change in heat. As there will be no change in heat, so heat exchange will be zero. So according to the formula of entropy, that is S, capital S is written as dq by dt. I have already discussed that S, capital S is can be written as dq by dt. So q is nothing but the change in heat. So as heat is changing, as heat is not changing, because in a turbine neither heat is coming from outside, no heat is escaping from that particular structure, so entropy will be zero. So we can say from 1 to 2 path we will be saying that it is your isoentropic path. Now from 2 to 3, not we are not going to next slide. Let's suppose first we'll discuss from 2 to 3 in the condenser, what will be the path, what will be the process, we can say. Let's discuss. In 2 to 3 it will be isobaric heat rejection, an isobaric process in which pressure of the working fluid remains constant. So what we'll be doing, that in the 2 to 3 process we'll want to keep the pressure of a particular condenser constant, but it will reduce slightly because we are using condenser, we are taking out the heat from it, but that heat we are taking out, it will not going to change its particular temperature much because we are taking the latent heat out of it. From 2 to 3 you will say that if we are condensing it, we are changing its heat, we are cooling it down, how the pressure is not changing? Because what the temperature, the heat that we are taking out from the condenser is only the heat that we are taking out from the temperature is only the latent heat. So as latent heat has been taken out, there will be no change in the pressure because pressure will be dependent on the temperature. If temperature changes, pressure will change. But in the process from 2 to 3 line in which condenser is coming, only latent heat has been extracted out. Due to the extraction of latent heat, your steam will be turned down into, or it will be converted into water vapor. So as it will be converted into water vapor, but temperature will remain constant, and hence as temperature is remains constant, it will be again the case that your pressure will be constant. That's why this process or this line or this path of 2 to 3 is known as isobaric process. But again, what do you think? I'm again posing a question that I will going to give you answer because no one is in front of me, but I am posing a question that what do you think will be the effect in the entropy in the path of 2 to 3? What is my question? In a path from 2 to 3 in which condenser is coming, what do you think will be the condition for entropy? It will going to increase, it will going to decrease, or it will going to be a constant, or it will be zero? But what we have discussed in entropy, that according to the formula of entropy, capital S is equal to dq by dt. So as in condenser it is extracting out heat, I am again repeating that in the condenser it is extracting out heat. So we are taking it out, we are taking out the heat, we are taking out the latent heat, keeping the temperature constant, but it's the state of water or state of steam is being changed to water state. As the state is changing, we are extracting some heat out of it, so we can say that entropy will going to be reduced. So what will be the answer? In 2 to 3 path, the entropy will be reduced because heat is being extracted out, and that heat is nothing but the latent heat. That's why the temperature is constant, and hence the temperature is constant, pressure will be also constant. So the process in 2 to 3 path in which condenser is coming is isobaric process, and it is isobaric process means pressure is constant but entropy will reduce drastically. Okay, in coming back to 3 to 4 path, again going to 3 to 4 path. In 3 to 4 path, it is again writing that it is isoentropic compression. During the isoentropic compression process, external work is done on the working fluid by means of pumping operation. Again what we are saying, that in the feed pump, in the path of 3 to 4, We are discussing figure 1a only, so you will be always concentrating on figure 1a. Don't look at figure 1b. I will be discussing figure 1b explicitly after this discussion. So coming back to the path, that is the path that we are discussing is 3 to 4. In 3 to 4 path, what is coming, what is the essential component is coming in between? It is nothing but the feed pump. As the feed pump is coming, we are saying that again the process will be isoentropic process. Why it will be isoentropic process? Because isoentropic, we are talking, isoentropic is nothing but the entropy will be constant. How entropy will be constant? Why? Because in the feed pump we are just increasing the pressure. If we are increasing the pressure, why? Because due to the in the condenser, some of, you can say, ideally there will be no drop in the pressure, but as your it is being converted in from one state to another, some pressure drop will be there. So feed pump will be there to increase the some amount of pressure, because inside the boiler which is operating at very high pressure, so you cannot feed it with low pressure low temperature liquid. Otherwise in the boiler there will be a good, or there will be a big crack, or it can be catastrophic also. Okay, so we should be having a feed pump, so that feed pump will going to increase the pressure. But it is in the feed pump, it is nothing but feed pump, you can, in a layman's language you can say, it is just the opposite of steam turbine. Feed pump is nothing but the opposite of steam turbine. What is happening inside the steam turbine? It is just extracting the extracting the energy out of the particular it is extracting the energy out of the particular steam, and it is letting that steam to expand without any change in the heat, without any change in the latent heat. Similarly in the feed pump, it is again increasing the pressure of a particular gas by compressing it. It is the compression process over here in the pump, where in the turbine it is the expansion process. But in both the components, in both these essential components, there is no exchange of heat. I'm again repeating, in both these essential components, that is in feed pump and steam turbine, there is no exchange of heat. As there is no exchange of heat, again I'm repeating, entropy will be constant, because capital S, that is nothing but entropy, is equal to dq by d capital T. What is dq? Q is nothing but the heat exchange. But as in feed pump there is no heat exchange, there will be no change in the particular entropy. Okay, and after that feed pump, again it will be fed back into a boiler. That is 4 to 1 path. So again, going to the next slide, 4 to 1 path will be the isobaric heat supply, steam generator or boiler. During this process, the heat from the high temperature source is added to the working fluid to convert into a superheated steam. So what we will be having in this block diagram, if you have already studied thermal power plant, you can see that after feed pump there will be always a economizer. Why economizer will be there? So that economizer will going to increase the temperature of that particular fluid, because in the condenser temperature will be heat has been taken out, so temperature will be dropped, but it will not be dropped in a very drastic manner, so that your pressure will be changed. Because what we will be discussing over here will be the ideal case, but in practical cases there will be drop in temperature, there will be drop in pressure, but somehow we can say that process will be very much nearer to the isoentropic process. So what you can see in this particular closed loop structure or closed loop process of thermal power plant, according to thermodynamics pattern, that there are two processes going on simultaneously. One process is isobaric, that is in which pressure is constant, and another is isoentropic process, that is nothing but the in which entropy is constant. This can be also understood by the figure 1b. Which is nothing but the graph between T and S. What is T? T is temperature. What is S? S is nothing but the entropy. So what is this? This TS graph is nothing but the Rankine cycle, or what we have discussed in the previous particular closed loop cycle is nothing but the Rankine cycle. That is the cycle in which what is the working fluid? We are working on that. The working fluid is water. So water is converting back into steam. Again, steam is converted into water. By keeping a pressure constant, by keeping an entropy constant for different patterns from different paths, and performing a particular cycle, that cycle is known as Rankine cycle. That's this particular process of thermal power plant is based is working on a principle of Rankine cycle. So coming to figure 1b, in which we have plotted a curve between you can see a dome shaped curve. This is a standard shaped curve that you will be always getting between T and S for a working fluid water. So this point you have to remember, because I will not be going much deeper into the thermodynamics, because that is not much required for you all, as you are all the electrical engineering student. You should remember this, that in a TS graph of water as a fluid, in TS graph of water as a fluid, this dome shaped structure will be there. But what will be the meaning of this dome shaped structure? Inside the dome, you have to remember that you will be considering liquid plus vapor. Inside the dome, you can say that this is a dome shaped structure. So inside the dome, it will be L plus V, that is liquid plus vapor will be existing. Left of side of the dome means you can see the boundary of from the left hand side. So as you are sitting in front of your laptops, so your left hand side pointing the left boundary of the dome shape. So if you are considering all the portion out of that boundary, we are not considering inside the dome. I am want to consider all the area outside the dome. So in the left hand boundary, all the area outside the dome will be nothing but the liquid. So we are having liquid there. Then we are having the boundary of left hand side boundary of a particular dome shaped structure of TS graph. Inside the dome, we are having liquid plus vapor, and the right hand side boundary of the dome shape, and the area outside it where the superheater is written, where the superheater is written, that area is known as steam or vapor. So what three portions we are having? So we are having liquid. So we are having liquid, and then we are having inside the dome, we are having a particular liquid plus vapor, and outside the right hand side boundary, we are having the steam. So the thing superheater where it is written, it is all area, we can say it is nothing but the steam. The economizer where it is written, so inside the TS graph, if I want to consider, the area will be nothing but the liquid, and inside the dome, it will be nothing but the liquid plus vapor. Inside the dome, it will be nothing but liquid plus vapor. So let's suppose, if you want to understand this, so let's suppose you are standing at point A, at this boundary. So all of you can see that notation capital A. So let's suppose you are you are at point A. So point A means, as comparing with the previous block diagram, at point A means that you are inside the boiler. You are inside the boiler. So what will happen inside the boiler? Inside the boiler, you will going to increase the temperature, and let's suppose you have increased the temperature and you have reached till point A, and that point temperature you have increased is being now constant. Why it is constant now? Because you are continuously increasing temperature. It is being kept constant because you have already assumed that your water has been boiled. The water has been boiled and it has been reached up to very high temperature at a very high pressure, where it has been at the verge of conversion from liquid to vapor, where it is at the verge of conversion of liquid to vapor. So as the states is converting from one state to another, at that verge of conversion of a state from one state to another, the temperature will be constant. So let's suppose you are moving in that path. So what you are doing, from A you are going to B in a left to right. You can see the B notation also. So A to B, you are working inside the boiler only. A to B, you are again working inside the boiler because your temperature is constant. After the boiler, where will steam will going to go? Steam have to go to turbine, but in between, before going to turbine, you will be always knowing that in between a turbine and a boiler, there will be a superheater. You should know that because you have already completed thermal power generation. In between a boiler and turbine, there will be a superheater. Why superheater will be there? Because why? Because if let's suppose you have heated your particular fluid at a boiling point of that temperature, but as soon as that fluid will be coming out of the boiler and it will be entering into a turbine, suddenly the temperature will certainly drop and it will be again converted into liquid. Certainly the temperature will going to drop, and again it will be in a no time it will be converted into liquid. So as soon as it will be converted into the liquid, it will going to impinge the blades of the steam turbine. It will going to corrode that particular blades. So what we want to do, we want to increase the temperatures furthermore. we want to increase the temperature furthermore, not inside the boiler. We are not doing inside the boiler because pressure will be also the constant, because we are increasing the temperature, pressure will going to also change. So we cannot do this inside the boiler because boiler area is somewhat, you can say, will be predefined. We cannot again start heating it, otherwise it will be, it can be the case that thermal stress can occur. So what we'll be doing, we'll be having a superheater component will be placed in between boiler and steam turbine, where your steam will be again heated up to a certain amount of temperature. So you can see from B to C there is an increase in temperature, and as you are increasing temperature you are employing certain heat from outside, so there will be certain change in the entropy also. So it is a linear graph from B to C, but that B to C is only there because due to the superheater, because in superheater temperature is quite increased. Now from C to D it is written that this path is corresponding to steam turbine or turbine. We have already discussed that in steam turbine there will be no exchange of heat. In steam turbine there will be no exchange of heat. It will be only your gas, your vapor will be, or your water gas, and you can say water vapor will be allowed to expand, and it will be your temperature will be extracted out from it, but there will be no loss of temperature, there will be no loss of heat, because it will be lossless structure built, that is of turbine. In an ideal case I am talking about. So as no heat is being added up, as no heat is being taken out of it, so we can say that in the turbine process there will be no change in entropy. So entropy will be constant from C to D, but there will be a drastic change in the temperature. Your temperature will going to reduce, but this temperature that is being reduced is not that temperature of dq by dt of the formula of entropy. It is nothing but the reduce in the latent heat. It is nothing but the reduce in the latent heat, because what we are talking in steam turbine, all the energy will be extracted out, so your steam will be converted into water. So latent heat has been changed, but that heat has not been extracted out. So we can say that temperature will be going down, but your entropy will not going to change. Because steam has been converted into water and there is no exchange of heat, because we have already talked that in turbine there will be no exchange of heat. So due to this, the C to D will be a vertical line, and that vertical line corresponds that temperature will be reduced, but your entropy will not change. But let's suppose at this point D is very much closer to the boundary of steam and, or you can say, vapor and liquid plus vapor. So if you are continuously decreasing or you are continuously extracting out the energy in the turbine, your temperature will be falling, but entropy will be constant. So after D, what you will be doing, you will be having a condenser. So after expansion, particular amount of expansion as much allowed in the steam turbine, the steam will going to enter into a condenser, where it will be converted into water. Your steam will be converted into water, but where the steam will be converted into water, there will be no change in temperature, because you will be taking out only the latent heat. In steam turbine, temperature is changing, there is no change in the heat, there is no change in the latent heat. That's why steam is converting into water, or your steam will be there only, it will not be converted into water. Steam will be there, but that steam, superheated steam, will be cooled down, but there is no change in state. As there is no change in state, we can again interpret that there is no exchange of latent heat. So you have to remember that if there will be a change in state, then only there will be change in latent heat. So in the turbine there will be no change of latent heat, only due to the expansion your steam will be cooled down from the superheated state. It will be in the state of steam only. That's why temperature will reduce, but entropy will be constant. But at point D, when it will start entering inside the condenser, it will be converting back into water. So in condenser, we have already talked about that in condenser we are taking out the heat, and that heat is nothing but the latent heat, but temperature will not. But in this case, temperature will not going to change, because we are just only changing the state of a particular fluid. That means that your cooled steam is being now converted into cooled water. but temperature is constant, but state has been changed. That state has been changed due to the change in the latent heat. So you should be very cautious that I am talking about sometime I am talking about the temperature, and sometime I will talking about the latent heat. So I am making it more clear that by changing the latent heat, temperature will not going to be affected much. In ideal case, it will not be affected any amount, but in practical it will be affected little bit. But by changing the latent heat, only the state of a particular इस फ्लूइड विल गोइंग टू चेंज. बहुत सिंपली अगर मैं बात करूँ, अगर आपके पास एक बर्फ़ का टुकड़ा है, अब बर्फ़ के टुकड़े को मेल्ट हो जाता है तो पानी फॉर्म होता है, तो पानी का जो टेम्परेचर होगा, जो बर्फ़ का टुकड़े का टेम्परेचर होगा, एकदम एक ही इंस्टेंट पे बिल्कुल सेम ही होगा. आई थिंक आई एम क्लियर. एक बर्फ़ का पीस है और तुरंत मेल्ट होकर अगर जो पानी फॉर्म हुआ है तो उसका जो टेम्परेचर और जो बर्फ़ का टेम्परेचर है वो बिल्कुल सेम है. बट योर स्टेट हैज़ बीन चेंज फ्रॉम आइस टू वाटर, सो दैट चेंज इन state is due to the change in the latent heat, but temperature is constant. So that concept is being applied over here. So from D to E in condenser, temperature will be constant, but your state will be changed by the extraction of certain amount of heat, that is nothing but the latent heat. So from D to E process, you can say it is the condenser process in which your entropy will be decreasing because you are taking out or you are extracting out latent heat, but temperature will be constant. So you should remember that example that I have discussed of barf ka tukda and water. Okay, that is very important example, you can say. After the point E, the next notation is F. So from E to F, you are having the feed pump. We have already discussed that feed pump is nothing but the replica of steam turbine, opposite replica of steam turbine. In steam turbine we are expanding, in feed pump we are compressing. As steam turbine we are expanding, there is no change of heat, but in feed pump we are compressing, again there will be no change of latent heat. So what we will be saying, you can see that as we have discussed in C to D, in turbine there will be no change in entropy because we are there is no change of latent heat. Similarly, if from E to F there will be again a small vertical line, there will be no change in heat. So again the entropy will be constant from E to F also, because your feed pump is nothing but the replica of steam turbine. Okay, again after F to A, that is not F to A, what will be the part? It is written economizer. So you already know that after the feed pump there will be a economizer. Why economizer will be there? Because as you have cooled down your in the turbine, your steam has been decreased in the temperature, but inside the boiler the water is available or the steam is available at very high temperature, so you cannot feed back that cooled or less temperature water directly inside the boiler. So you need economizer, so that it will going to increase the heat certain amount of time, or it will going to increase that temperature. I will not say heat, it will going to increase the temperature, so that it will going to match the temperature available inside the boiler, because you have already matched the pressure through feed pump, because feed pump will be increasing the pressure, so pressure will be matched inside the boiler. But how you will going to match the temperature? So temperature will be matched through a economizer. So if you are increasing the temperature, you are applying certain amount of heat from outside, so there will be again a linear line in which temperature will be also changing and entropy will be also changing, and you are coming again back at point A. So F to A will be depending on the economizer. So this is a closed path that is starting from A to B to C to D, E, F and A will be comprising of all the essential components of thermal power plant. And this cycle, this recyclable or this closed loop cycle is nothing but the Rankine cycle, which is very important to understand the Rankine cycle. And the working fluid which will be responsible for this Rankine cycle is, or the T in the TS diagram, the graph is responsible on which fluid? The fluid is water. So if you are using another fluid, this TS graph will going to change. You will not be having this dome shaped structure, because this dome shaped structure is only for the working fluid as water only. Okay, so I think that I am very much clear, or very much I have given very much effort in explaining that figure 1 and 1A and 1B, which is very much quite reflected to it. The thing that I have discussed is given in the explanation in this particular slide. This diagram, if we are coming back to slide, is again the same diagram that we have discussed in the previous slides. In this This is incomplete. Why it is incomplete? Because in between steam turbine and turbine it is okay. In steam generator and turbine, in between steam generator and turbine there should be a superheater, and after pump there should be economizer. Then it will going to become a complete block diagram of a thermal power plant. Again I am saying it will be the complete. Am I correct? It will be the complete? No, it will not be complete, because superheater, after superheater there should be again one more thing, that is air preheater. So after steam generator there will be a superheater, then air preheater, then turbine, then condenser, then pump, then economizer, and then again coming back into the boiler, or nothing but the steam generator. That process will be how it will be how it is being related to the thermodynamics, or how it is related with the Rankine cycle, that I have discussed using these two diagram, these two block diagrams, and the curve, that is a TS curve, that is nothing but the temperature and entropy curve, in a very explicit manner. For your reference I have already kept all the explanation in a very, you can say, in a very explicit manner, so you can study these things from the slide. And if you are facing any amount of problem in a particular step or in a particular path, you can again write it to me in a particular doubts sharing sheet that has been shared along with you, in which you are very much active. So you will be always be welcomed if you are having any amount of doubt. If you want to float a doubt through a mail, you are also welcomed. Okay, but the main point of concern in this particular lecture is that you should be very cautious that temperature is one thing and heat exchange is another thing. So don't mix your latent heat with temperature, and always remember that example of small टुकड़ा of बर्फ and conversion of it into a water. So अगर बर्फ़ रहेगा, बर्फ़ तुरंत मेल्ट होकर पानी में कन्वर्ट होगा, तो पानी का टेम्परेचर, बर्फ़ जो पहले रहा उसका टेम्परेचर ऑलमोस्ट सेम रहेगा. बट बर्फ़ से वाटर बन गया, स्टेट चेंज हो गया, तो रैंडमनेस बढ़ गई, तो एंट्रोपी चेंज होगा, बट टेम्परेचर नहीं चेंज होगा. ओके, so this much will be the lecture, and that is hopefully will be the last lecture from my side in this particular semester. That is already all the topics, almost all the topics have been covered explicitly. If you are having any amount of doubt, you can again float it to me in that particular Excel sheet. Darshit sir is again floating some lectures, and more lectures will be taken on distribution system, that is on the AC distribution, DC distribution, that will going to cover your topic of distribution system too. So study well, stay calm, stay safe, and prepare for your examination. And hopefully in the next week there will be one more quiz. So I am giving you a small syllabus for that in this slide. I will be mailing you to all also, that in that the portion that I will be covering will be after the classes, and the most question will be from the insulators, substations, tariffs, and the portion that we have discussed through video lectures. Okay, prepare it. It will be good for you. That will not be the part for C assessment, but it will be beneficial to you. Thank you very much.